And so I will give this 45 minutes tutorial on explainable AI. And yeah, so this is the structure of the tutorial for today. It will be decomposed in 3 parts. First, I will briefly introduce what are the motivations for explainable AI. And then I will show some typical approaches to explainable AI, like explanation paradigms. And finally, discuss a little bit some more advanced methods that can achieve things that classical approaches cannot. And yeah, so let's start immediately with comparison between standard machine learning and explainable machine learning. So what explainable machine learning, in which way it differs from standard machine learning. And in standard machine learning, the typical pipeline is that you have some data, supervised data, then you train a machine learning model, and then based on this machine learning model, you can perform predictions, either of the existing data or of new data. So basically, it has to generalize to new data points. And with explainable machine learning, you add the human in the loop. So basically, you are trying to start from the machine learning model and build some interpretability into this machine learning model. For example, returning some kind of visualization of what the machine learning model does. The human can inspect this visualization to verify that the strategy of the machine learning model that the strategy of the machine learning model is consistent with the human own domain knowledge. And it can either then just return the verified prediction, that basically the prediction was supported by the right features, or identify some flaw of the model and then try to address that, for example, by either directly correcting the machine learning model or providing more data that would then correct this flaw. So this is an example of a explanation. So typically you have like an image which is received by some classifier. So here the classifier is assumed to be trained, for example, a neural network for image recognition. And then this neural network, let's assume that it produces high evidence for the class viaduct. And then the idea is to try to identify, or the explainability technique, explainability module, will try to identify pixels that have contributed for or against that prediction. And this is the kind of heat map you would typically get, where a red pixel, basically red highlighting, corresponds to what contributes in favor of the class viaduct according to the model, and blue pixels corresponds to what might be contradictory with the model's own prediction. So one thing which is important to note is that it is not necessarily optimal that the explanation technique highlights the actual object, because what we expect from an explanation technique is not that it actually finds the object in the image, is that it exposes the decision strategy of the model. So if the model is flawed, for example, it's based its decision on maybe the grass, because somehow the grass and the viaduct are always correlated, this should be revealed through your explanation. And so just like looking at overlap between explanation and actual objects is not a proper way of verifying that the explanation technique works well. Okay, now let's come to the motivation. So why do we want explainable AI? And there are roughly 4 main motivations for explainable AI. The first one is to try to build more trustworthy machine learning models. And here, XAI, for example, can be used to further validate the machine learning model. For example, to verify that it implements the correct decision strategy. For example, it looks actually at the object in the image and not at some spurious correlated feature. And as a consequence, we might expect that it generalizes well. So that's one of the main usages of explainable AI, trying to build more reliable models, or try to identify flaws of models in order to eliminate these flaws. But there are many more practical motivations, and one application, what potential application, is using explainable AI to generate scientific insights. So here, you might think of, for example, a model which, instead of predicting something which we know, might predict something which is actually some very technical concept, and nobody has a clue how to predict. What is the strategy for predicting this thing into something technical? And here, what XAI might do for us is to identify variables in the input domain, which actually are predictive of this concept that we don't really understand. And that can be, for example, some variables in some complex system, for example, molecular system or some biological cell. That's one more motivation. Another one is to try to ensure some compliance into the AI system. So more and more, there are some legal frameworks that require AI models to come to equip decisions with explanations. And basically, in that case, explainable AI is kind of a requirement for deployment of the AI system in practical applications. And finally, a last one is actionable AI. And the goal of XAI, so basically what XAI can do is to identify kind of what are the relation between input and output features. And if this is well understood, then and if the machine learning model is kind of predicting some properties of a complex system, this kind of correlation that have been identified can be used to understand how to actionate a machine learning model or a system in a meaningful manner. I will not go into depth for the last three. I will rather just highlight the trustworthy AI aspect with an example, which you might already have seen. This is a data set, Pascal VOC 2017. It was one of the popular data set for computer vision 10 years ago. And it is composed of different classes. And here you have the test set performance of two models, a model based on Fisher vectors and a deep neural network pre-trained on ImageNet. So what we can observe is that in general, the deep neural network is performing significantly above the model based on Fisher vectors, which is a shallow model, especially on some classes like the cat or the dog. The difference is very high. And what we observe is that also on some other classes, for example, let's say the horse, then the performance of the Fisher vector and the deep model is roughly the same. So would that be a question of overfitting? No, this is not overfitting, because we are here measuring the performance on the test sets. So this is really like the output of some standard validation procedure. And now if we look at the explanation that our explanation technique has produced for the decision of these two models, this is what we observe. The Fisher classifier is actually not looking at the horse to support the classification into horse, but is looking at some copyright tag at the bottom left of the image. And basically what the neural network does here is not to predict based on the right features, but exploiting some spurious correlation in the data in order to artificially improve its performance. And what is important to note is that it is not overfitting. It's not just like something which is in the training data. This spurious correlation is present both in the training and in the test data. So even if you are doing the proper training and test splitting of your data, you will still be affected by this spurious correlation, and it will still remain undetectable by just looking at the test set accuracy. So here you really need to get something additional, and the explanation of the decision provides a way of finding that out. Okay, and so basically what is the problem of this spurious correlation? Well, you can imagine that now some images that are where the horse is not so easily detectable, if you remove the copyright tag, they might artificially go down into not being detected as a horse. And you might have the opposite case where you have something which is not a horse, but as soon as you add some copyright tag, then it becomes a horse according to the model. And we call this type of classifiers, which rely on spurious correlation, clever hands classifiers. And this clever hands classifier, they might work well exactly in the setting they are currently being used, but they are unlikely to perform well on future data. Okay, so this was basically for the motivations. but let's look now a little bit more at the different explanation paradigms. And you can try to categorize explanations into different types of explanation, what you want about explanation, what it tells you about the model. And a first distinction can be made between a mechanistic and functional explanation, where basically in the case of mechanistic explanation, we would like to understand like how the neural network produce the explanation or the decision at the neuron level. So basically understanding like the internal of the decision process. While functional is rather interested simply in explaining the input-output behavior of the model. So if you want some kind of practical analogy, you could think of the mechanistic explanation as being like the mechanics, so the one who is actually repairing the car, and functional explanation as being the pilots who just want to understand how the relation between the inputs, the basically steering wheel, and the output, which is the trajectory the car will take. That's one possible distinction. Another one is between extracting a set of features which are relevant for the task or scoring different features. So this is one possibility. And lastly, local versus global. Basically, whether we are interested in explaining a particular prediction, for example, the prediction of a given image into some class, or if we would like to understand the behavior of the model as a whole, for example, on a whole data set or a whole input domain. Okay, so this is basically mechanistic versus functional. So basically, in the case of mechanistic, you will try to pay attention to the neurons to see basically how the features are being progressively built in order to achieve the decision you are interested to explain. While in the case of the functional explanation, then you will rather just want to think of this as a function, at least on a conceptual level, in order to identify how changing the inputs or basically which input contributes to the output. Regarding local versus global, this is the idea. So you have basically some input domain. Maybe you have some different classes. Let's say class 1 is in green, class 2 is in blue. And in the case of a global explanation, you will try to understand, like to characterize this whole domain in which the neural network reacts in a certain way. Whereas for a local explanation, you will focus on a specific data point and typically try to analyze how the function behaves around that specific data point. For example, to identify features to which the function strongly reacts in this location. And it might differ if you look at the function for this given input, for this given image, or if you are looking at the function for the one just above. But sometimes there are also some connections. And for example, while there used to be some strong distinction between local and global explanation, we've contributed some method, which we called a Freie, which basically allows us to recover some global explanation from multiple local explanations. And the idea is that if you have a data set and a fast explanation technique, you can basically compute an explanation of the class horse, for example, for every single data point. And this is basically what you get. So for every data point, you have like its own explanation, which indicates why the neural network believes there is a horse or not in the image. And then as a second step, we can take these explanations and do some clustering according to the heat map, and it will reveal some prototypical decision strategies of the model on the whole input, on the whole data set. And what we can find here, for example, is that you have kind of 4 clusters, and 2 of these clusters reveal what would be found anecdotally on one single image, which is that the Fisher vector model tends to look at the copyright tag to build its decision in favor of the class horse. And there is one more strategy which was not found beforehand, but which could be found by this analysis, is that the horse is also sometimes being classified because of these obstacles, which also seem to be typical of this data sets. So basically here we don't have to scan through all the different images and explanations, which might be invisible if you have a large data set, but you can instead run, like feed all the images of the data set into the machine learning model, produce explanation for all of them, and then just do clustering, and then you have kind of a structured way of looking at the explanation structure of your model and identified a potentially flawed strategy, and also have much less risk of missing a flawed strategy, because here you are looking really at every single data point in the data set. Okay, so this was for the introductory part, and now I will move to part 2, where we will just discuss a little bit different attribution methods, which are a specific type of explanation. So first, what do we mean by attribution? Attribution is basically taking the output of your model and try to decompose it in a way that identifies the contribution of the different input features to your prediction. So here, for example, you have this function f, which you can think of it as some amount of evidence for a certain concept. Here it's a concept motorbike. And then you would like to decompose this value into scores, which are basically the share for which feature x1 is responsible, the share for which feature x2 is responsible, and so on. And typically you would like if the classifier really detects the motorbike, that the scores for the wheels and so on are high, and the score in the background would be typically low. And so one among other property that needs to be satisfied is decomposition or conservation, which means that if you sum all the score of every input feature, then it should approximately match the value found at the output of your neural network. Okay, so now there's a lot of work that has been done on attribution methods, many approaches that have been proposed. And just to be, I mean, I cannot be exhaustive here, but like to just describe the main families of approaches, you have a perturbation-based approach where you take your function and you try to turn on and off some features and see how the function reacts. And there are basically a lot of methods based on occlusion. And one which is quite popular nowadays is the Shapley value, which has nice theoretical background. Otherwise, you have propagation-based approach where you think of the prediction as going forward in a graph, for example, a neural network, and then explanation as going backward in that graph until you reach the input features. And there are a variety of methods, for example, guided backprop or layer-wise relevant propagation, that have been proposed for that. And in this tutorial, I will focus mostly on Shapley value and layer-wise relevant propagation, try to identify what are the respective strengths and typical problem on which we would like to apply them. And there are a few more categories, and some of which try to build a surrogate model, which is simpler to analyze, which doesn't have all this nonlinearity, but which is basically has to be built locally for every data point. And finally, there are a few models that are called self-interpretable, because they are structured from the very onset to be interpretable, for example, to have like a summing over some special locations or other technique which makes interpretation easy. The self-interpretable models, they need to be, basically you need to kind of define the structure of the model before training, right? So if you have an existing model which you would like to explain, which does not have the specific interpretability structure, you cannot use that. You need to use one of the methods above. And finally, you have a lot of hybrid approaches, because as often none of the methods has like all the desirable property out of the box, and often it is necessary to combine things in a relatively in a subtle manner. Okay, so let's start with Shapley value. So in fact, Shapley value has a very deep, a very long history. It was first proposed in 1950s by Shapley in the context of game theory. And basically what they were asking as a problem is that if you have like some players that have played some game together and as a result obtain some profit, how should they share the profits between each other? No? So what Shapley proposed is that basically they should kind of imagine all the possible scenarios where they have been involved or not in the game and try to see how much profit they would have got in each scenario. And if you apply this idea, then you end up with a formula which is basically determining the share that player I should receive as being the sum over all the possible set of players that do not include player I. And then you have this difference, which is the effect on the reward, the effect on the function of adding player I to this current coalition. And then you have some weighting terms. Okay, so that's maybe a bit abstract. So let's continue with a practical example. Imagine that you have 3 players. Let's call them player 1, 2, and 3. And basically, they are basically 1 if they are in the game and 0 if they are out of the game. And we would like to basically, if all 3 are in the game, you have basically 1 times 1 plus 1. So you have basically 2, a reward of 2. And you would like to be able to decompose this reward of 2 on the 3 individual players. So if you look at this formula, then you can build this kind of table where you have these coefficients. And these coefficients are basically constant for a given set size. They are basically used to kind of balance the contribution associated with different set size. Basically, when you have a lot of elements or a lot of set of a given size, the alpha S will go down. And then you can look at this delta S, which is basically the contribution of adding the player to the current set. So let's start with phi 1. Imagine that so far we have no player in your coalition. And then, so basically x2 and x3 are equal to 0. And now you are adding x1. So we'll have like 1 times 0. And 1 times 0 is 0. So basically, if player 1 join alone and player 2 and 3 are out, it doesn't make any difference. So there is no added contribution. Now let's suppose that there is player 2, but player 3 is not participating. Then the effect of adding player 1 will be 1, because if player 1 is not there, you have basically 0 times 1. If player 1 is there, you have 1 times 1. So you have 1. The same happens if you only have player 3 in the coalition. And if you have both players in the coalition, then you have 2. Okay. Now you can do the same for phi 2. And you will basically get like this table, and the same for phi 3. Now what you can do, you can take this alpha S and delta S and then just like sum them up over all the coalitions. And you get for phi 1 a contribution of 1. For phi 2, you get a contribution of 0.5. And for phi 3, you receive also a contribution of 0.5. So what is interesting is that they actually receive something different. And what you can also observe is that x1, which has a very specific role here, receives more than x2 and x3. And there is a nice interpretation to this distinct attribution, is that x1 actually has more bargaining power. So if you think of x1, it can basically always like cancel all the reward by just withdrawing. So if you think of it in terms of negotiation, then it is kind of normal that x1 gets more, because it has this kind of critical role which can basically remove all the reward if it withdraws. You can think of someone in a company having a very specific specialized role might also earn more than someone who does not have such a critical role. Okay, so now, as you might observe, this sum is actually very large if you have not only 3 features, but many features. So if you have d features, you have an exponential number of terms in the sum. So one approach is to sample and instead of summing over this exponentially many terms of the sum, you will basically randomly sample some of these values. For example, here you have like kind of two rows, and you can just sample one and avoid like this combinatorial explosion. And this allows you to basically compute this explanation in terms of d times t features, where t is the sample size in every strata. So you still need to evaluate the function multiple times, in fact, still quite a lot of times if d is large, right? Especially if you want to use t, which is reasonably sufficient value of t, which is typically 10 or 100. So that remains relatively expensive, but also there are a few computational improvements that are possible. But yes, overall, it remains quite expensive to apply Shapley value, even Shapley value sampling on high-dimensional data and complex models. So what are the strengths of Shapley values? Is that it has a nice theoretical embedding or theoretical background, which is basically shown to be a unique solution given a certain number of axioms. And this was proven in some earlier work. And also, because of this nice theoretical embedding, it also yields a faithful explanation. So usually they are performing quite well compared to simpler approaches. But there is also this limitation of Shapley value explanations being computationally expensive. So now another approach is to move away from this perturbation-based explanation techniques to propagation-based explanation technique. And here the idea is to try to reuse the graph of the neural network in order to identify quickly what are the input features that have contributed the most to the prediction, ideally in a single forward-backward pass. And so here, instead of having to evaluate the function d times t times, you would like to evaluate the function only once. And so that would basically carry a big computational improvement. And what is difficult here is that you have to design the propagation process in a way which is meaningful. And what you will try to do is to build basically this in a way which is locally consistent. So that's the best we can do. For example, at every layer, if you redistribute between different neurons, you should have basically this conservation property, which is enforced. And you should also try to redistribute always to neurons that are considered locally the most relevant. And so we have developed a method for that, which is called layer-wise relevance propagation. And basically, it implements this idea of backpropagating from the output of the neural network to the inputs. And here is some notation first. So basically, you denote by J neurons in a given layer and K neurons in the next layer. And WJK, the neuron between the weight between two neurons of two different layers. These are like just some more notation. And you can write between two layers in a kind of generic way the activation of K as being some nonlinear function, typically the ReLU of the weighted activations in the layer below. This is the neuron equation. And now the idea is to define not functions that are mapping the signal forward, but functions that are mapping the signal backward, and we call them propagation rules, and they can be different propagation rules at different layers, depending on basically, for example, to optimize explanation quality. And typically they will have the following structure, this explanation rules. Basically, it is on the numerator, you have something here in red, which is the contribution of neuron AJ to the activation of the neuron AK in the next layer. And it can be, for example, AJ times the weight, but you can also have like slight variance, for example, to give advantage to the positive contributions. Then you have this thing in the denominator, which is the normalization factor, which will ensure locally the conservation property, or at least approximately enforce the conservation property. Then what you have on the right-hand side is basically RK, which is basically what has been so far attributed until neuron K. And if you put it all together, then basically you get an attribution score for neuron RJ in the layer below. So basically you sum over all the messages that are coming from the layer above, and you get basically your score in the layer below. And you have this property that the sum of Rj is approximately equal to the sum of the Rj's. So basically you can think of it as kind of current, which is electrical current, which is flowing from layer to layer until the input is reached. And then you basically get an attribution on the input features. Now there is something, you can make a slight reorganizing of the LRP rule. You can put basically the activations as a factor, and then you can think of this LRP rule as basically being like the product of an activation. So basically the more activation, basically of an activation, and this, which we can think of it as a sensitivity term, and you can think of a neuron being relevant if it is activated and if the neural network reacts to it, if the output of the model reacts to it. Okay, now these are typical explanations that we can get with LRP. And basically you can have to apply these rules at different layers. And depending on which rule you choose, you will get different quality of explanation. For example, if you apply this simple rule, which is called LRP0, which is basically kind of a basic LRP rule, you obtain something which is quite noisy, which in fact corresponds to propagating the gradient. And you can change the rule, you can apply something which is epsilon, which basically adds some term in the denominator, and it will have an effect of sparsifying your heat map. And you can apply this factor gamma, which I was just showing in the slide below. So basically a gamma which is non-zero, and it will tend to densify the explanation and also bias the explanation towards positive values. And in practice, if you want to get like something which is nicely interpretable and which carries kind of the decision strategy, it is often desirable to combine different propagation rules at different layers, and this is what you get, right? So this is what general recommendation. If you want to apply LRP, you need to carefully choose the propagation rule at different layers. Okay, so basically that was the part on different paradigms for attribution, and for the sake of time, I just focus on two of them. But of course, there are many more contributions, and I don't try to be exhaustive here. Okay, so now we will look at the last part of this tutorial, which is basically trying to go beyond classical attributions, and I will give some motivations why we want to do that. So just think now about the problem of explaining similarity. So you can think of having two images of a squirrel, and you would like to explain why these two images are similar. So does that make sense to produce a heat map in that scenario? And most likely not, because they are not similar because of a specific pixel. They are similar because of interconnection between specific part of the first image and specific part of the other image. So what you would like to be able to draw connection between the two images that basically are matching between features of the two images that explain the fact that, for example, there is two squirrels in these two images. So LRP or other explanation techniques typically are not designed to build this kind of higher order attributions in terms of pairs of features. And we developed a method which is called BiRP, which can do that. And so the idea is that you start with a standard LRP rule. So again, the reason why we want to use LRP is that we can basically compute explanation in a single backward pass, which is fast. And now we would like to say, okay, well, instead of attributing in terms of individual neurons, we'll propagate the contribution of pairs of neurons. So basically, this is the standard LRP rule, which has this form, which we have seen just before. And now instead, we would like to have like essentially products of features. So basically, this feature neuron J and J prime, where J and J prime are basically activations of the two different images we give as inputs, times like the product of these weights. And then you have this denominator, which is a double sum over input features. And basically, you can see that it mirrors a lot of the properties of the standard LRP explanation. But here you are really able to propagate contribution not of individual neurons, but of pairs of neurons. And when you reach the first layer, you basically get contribution of pairs of pixels. And this is what you want in order to produce these kinds of explanations. Okay, so this approach looks rather intuitive, but it has the problem that in fact you have to do this very large double sum. And if you have many activations, it is not very convenient. But what we could find is that in fact, this pairwise contribution can be rewritten as a product of many standard LRP explanation. So basically, you just take the features which you have just before your dot product, which is basically computing your similarity. And on top of basically every element of the dot product, you are basically computing LRP explanations. So basically, you get for every image like a collection of LRP explanations. And then you have this outer product, which basically gives you, instead of like, let's say, n explanation of p pixels and n explanation times p pixel, you have like p square scores, which basically correspond to this connection between different pixels that you can see here, right? And so basically, because there are a lot of such connection, you need to do a lot of pruning and post-processing to obtain some visually pleasant explanation, but this is the kind of thing we can get. So here you have basically images of different type of like different images that are all predicted to be pairwise similar, and you see the reason why these images are similar. For example, this is just self-similarity between two exactly the same image, like it highlight the ears and the eyes as being ground for high similarity. You can also give two different images, for example, here two birds, and here it looks at the actually eyes of the bird as being the reason why these two images are predicted to be similar. Same with airplane. You can see that the top, the front part, the cockpit, is the main reason for these two images being similar. Sometimes you have also some surprises. So here, for example, there are two cows, and I think what you can observe is that in fact it doesn't find similarity due to the two cows, but because of the white calf which you have here in the first image. And in some cases, you really have like predicted high similarity, but the image is very cluttered and you don't really get anything meaningful out of it. Okay, so now why we have developed this, this method in the first place, it was basically to try to understand similarity in a project related to digital humanities, where we wanted to predict similarity between different illustrations in historical textbooks, to draw connection between these historical textbooks. And we have basically extracted a lot of images from these textbooks and tried to predict their similarity. And for example, we found that these two images were predicted to be highly similar. And of course, what we would like ideally is that the similarity is indeed supported by the objects in the image. But what we found out is that the reason for the high similarity was due to something unexpected, which is that there is basically this two little circle at the very middle of the image. So even though from the model, it looks like the model has learned from the score, similarity score, it looks like the model has learned to kind of rotate the image and to share and to identify this identical concept. In fact, it has nothing, it has learned nothing of that. It has just learned to match something which was occasionally constant between these two images, which was basically this thing in the middle. So basically here we are again faced with a kind of clever hands type behavior where the model performs well, but not for the correct reasons. All right, now I will just very quickly mention some of our recent work, which is basically about to be submitted. It is basically on trying to produce disentangled explanations. So here, so far, for every prediction, we have only extracted a single heat map, which identifies the important pixels. But in practice, this heat map might hide the fact that there are multiple sub-strategies that are used for predicting the overall image. And what we have proposed is to combine explainable AI and representation learning in some latent layer of the model to build this kind of expanded heat maps where basically the heat map can be now decomposed into different subspaces that indicate the contribution of various sub-strategies to the overall classification strategy. So here it's some images classified into basketball, and this is the typical heat map that we can get with, for example, LRP. And you see a lot of basketball type features, but you have in fact a lot of different features that are predictive of basketball. And now what you can do, you can try to apply this analysis into multiple subspace and essentially filter the explanation to pass through these multiple blocks that correspond to different concepts. And this is what you get. So basically you get like one explanation, one explanation for the sub-strategy looking at the marking lines on the floor. You have here the clothing of the basketball players. Here you have the heads, and in the last column you have the ball. So can be also quite useful when you have, for example, overlapping concepts where multiple concepts are actually present at the same location. You can kind of disambiguate what is the true reason why a certain pixel contributes to the prediction, for example, whether it is because of concepts, whether it's because of the head, for example, or because it is of the clothing. And then we look again at the clever hands scenario with this approach. And here we look, for example, a class of ImageNet, which is also known to have this kind of watermarks. And again, we look at we compute explanation for different concepts built on this watermark and cartoon class example. And what we could identify is that basically many of these concepts were predicting of the cartoon, sometimes the border, sometimes the small marking on the cartoon. But there was this last concept, which was actually reactive to the watermark which you have in the background and which is not intrinsically correlated to the class cartoon just on these data sets, right? So what we thought is that, okay, well, let's just, because basically we have this additive property where if you sum all these heat maps, you get back to the original heat map, and the heat map itself is a some decomposition of the prediction score. We can just prune this column and build or refine model to just basically take into consideration these sub-strategies. And if we do that, and you look at Poisson data, which has basically watermark, but not on the cartoon, but everywhere, or at least with 25% chance, then the error will, to some extent, decrease, and you will basically achieve a refinement of your original model. Okay, so basically that's what I wanted to present today. If you are interested in our work, you can check our review paper, which was published in 2021. So it has a lot of the recent work we have done included. And also for the most recent updates, you can check our website, heatmapping.org. It has some our list of publication, but also online demos and tutorials. You can also find some code as well as some software. So with this, I'm done, and I will be happy to answer questions.